Ladies, it's S and S nail powder, right?
No, it's
S,
not.
yes, S and S.
But it's R and S. R and S.
R and S.
S and S nail powder.
I know I got the right.
This is a summary of the
I checked.
alkyne reactions here.
I checked.
Okay, one thing we'll see about alkyne reactions is very similar to alkene reactions. Very similar. We'll see lots of the same reagents like BH3, okay, bromine. We'll see a couple of new reactions. The reactions are very similar. We have a pi bond. Pi bond's a source of reactivity. We've got two pi bonds. So it's going to be twice the fun, okay? We will react an alkyne triple bond with HX. We'll add HX to the pi bond to get an alkene. But then we can actually do it again because you can react an alkene with HX, and so you can react it twice the fun. Where are you going to make cation at? Right or left? Over here where the H is on the carbon, or where you got this extra alkyl group on the carbon? Over here, it'd be more substituted. Same questions. Okay? And so cation would be on the left. That's why the halogen is up on the left carbon. All right, here's your outline. We will hydrate alkynes. New term, new process called taumerization. We'll actually make a ketone. Well, that's specific. We'll make a carbonyl compound and maybe an aldehyde or ketone. Taumerization. We'll use hydrogen. Okay, lots of similarities. There's some drugs with alkynes and alkenes. Nomenclature. Okay, alkene nomenclature is covered by video, including E and Z terminology. Yeah, any questions there? E and Z terminology. I'll do alkyne nomenclature here. Very straightforward, similar to all other nomenclature. First off, two different alkynes. This is called a terminal alkyne, when the carbon is at the end of a chain and it thus has an H attached. Terminal. This would be an internal alkyne. That is, neither carbon of the alkyne has an H because it's not at the end. Okay? Terminal versus internal. Pretty straightforward. Nomenclature. Name of this alkyne. First off, you recognize it's an alkyne. Okay? Yes, it has alkane carbons or saturated carbons, but the unique functional group, the triple bond, takes precedence. We name it as an alkyne. We have prefixes. Well, you can't have a methyne because you have to have two carbons to have an alkyne. Just like you can't have methane because you have to have two carbons to make an alkene. But you can't have methane because you only need one carbon to be CH4. Okay? So you can maybe we'll have a, ine is our ending. We can have maybe butyne, hexyne, octyne. Okay? Longest continuous chain here. Well, it's 1, 2, 3, 4, 5. That's linear. Make sure you count all carbons there. It's common to miss a carbon. It's linear through there, right? Each carbon is sp hybridized, linear. So it's drawn linear. Longest continuous chain. How many? 5. So it's pent. Pent what? Pent. Ine. Okay, we're naming that in here, yeah? Pentyne. But that's pentyne. What is this? What is that? This is also pentyne. How can we distinguish these two, this one and the first one? Where's the double bond located? Or in this case, triple bond. Just like alkenes, triple bonds located where? Between which carbons?
Second.
Between 1 and 2, we just note the first position. So this is what? 1 pentyne, and this over here is 2 pentyne. What would this be? 3. Right? What is this?
2 pentyne.
3 pentyne?
2 pentyne.
Yeah?
2.
Yes, there's no such thing as 3 pentyne. Okay? Trick question. No such thing as 3 pentyne. Both of those are 2 pentyne. It's just flipped around. Right? 1, 2. Functional group at the 2, 3. Functional group at the 2, 3. Everybody good? Okay. What's the name of the next compound? Longest continuous chain. 7. That's the name. Alkyne. Where's the triple bond? 3. There's no such thing as 3 pentynes, but there is such thing as 3 heptynes. Everybody good? Okay. What if I stuck a chlorine right here and gave you a projection like that? What would the name of that compound be? Do we need anything else? Can we clarify it further? And what is it? S. Compound name is there, yeah? Isn't that S? Indeed it is. There you go. Right? Okay. Alkyne nomenclature. Pretty straightforward. Question. Is the alkyne, is the triple bond stereogenic? Can I draw a stereoisomer with this alkyne? Like I can with some alkenes? No, it's linear. Alkynes are not stereogenic. There's no stereochemistry possible with alkynes. Right? What am I going to do? It's not like one group is up and one group is down off of these 2 carbons. No, it's all linear. Yeah. Alkynes are not stereogenic. Okay, reactions. Electrophilic additions, just as with alkenes, except twice the fun. And a few additional considerations. Reaction with 2 molar equivalents of HCl, or HBr, basically HX. We have H plus, Cl minus. We can just show it ionic. Okay, my bond will attack H plus. Where are we going to leave cation at, right or left?
Left.
Left, where we have this extra alkyl group, so this attacks, these electrons attack there. And we get, okay, we've got to be careful here. This becomes double bond, because what, it was triple. It was triple, right? But 1 pi bond moved away and went and made bond to H. New bond to H. I'll draw in the old one. 1H there, now 2. Over here. This is where we have to be careful, because I tend to want to draw it like this. 3 carbons. What's here on this carbon now for my mechanism? Yes, that's right, carbocation, right? Pi bond breaks away, just like alkenes, except instead of going from double bond to single bond, we went from triple to double. Right? Question though, what's the hybridization geometry of this carbocation? Double bonded carbocation. Hybridization? SP geometry? SP is linear. I didn't draw it linear. Okay? Don't do this in your notes. It should have been linear. through there. That carbon linear. Yes, indeed. And we can leave it like that if you want to change it. Basically, I'm not going to draw it exactly how it should be. I tend to want to draw it as double bonded, a trigonal planar with a bond angle of 120. Specifically, though, you need to know if you were adding, yeah, it's SP linear. Okay? So I'll keep it linear. It doesn't matter. Unless you were asked. And the mechanism, it's not going to be critical to show correct bond angles. We like to not have ugly looking bond angles. Okay, carbocation. What attacks the carbocation? Well, these electrons from the chloride and bam. What does that give? Well, it gives product, right? Chlorine's now bonded there. That's truly now trigonal planar. We got good bond angles there. And there's your product. We added HCl to the alkyne, but in a regiospecific manner. The chlorine is not going to be on the end carbon. The chlorine is going to be where the carbocation would form. The carbocation is going to form here because it's got a rich alkyne ring. Yeah? Same discussion. Okay. But guess what? That product's an alkene. It can react. Can alkenes react with HCl?
Yeah.
Yes, that's one of the first reactions we did. So they can just react again. So a second equivalent, and where are you going to make cation at? Left or right?
Left.
Correct, on the left. So this attacks H+. These electrons swing out this way, leaving cation. There. New H there, yeah. And we'll look here. How do you get the final product with two chlorines there? Well, the other Cl minus then just adds here. And that gives you your product. Straightforward. This is called a geminal dihalide. What does geminal mean? Gemini. Twins. Two chlorines on the same carbon. Two halogens on the same carbon, called geminal. What if they were on adjacent carbons, next door to each other? Huh? What? Fraternal? Fraternal?
I don't know what that
No, if they were next door to each other, it'd be called vicinal. And that term was in your previous handout, right? Yeah? Vicinal, like vicinity. Okay, your neighbors live in a similar vicinity. They live in the same house, similar vicinity. Vicinal is geminal. Okay, geminal dihalide. If we had two equivalents, okay, two molar equivalents of HX. Along the way, we make the halogenated alkene. The question, though, is why do we make cation here? Well, you could say because this is secondary, right? Two carbons. If we had made cation there, it would have been primary, not as good. There's another reason we made cation there, though.
Resonance?
Who's it?
Favor?
Did you get 100?
Resonance.
Resonance. Have you been reading ahead?
Yeah, let's go with the answer.
Okay. All right. Don't read ahead. If you read ahead, then I run off. Okay. Resonance. Here we go. Resonance. Have we talked about resonance? A little bit. Resonance will be officially covered for test 3, but we're going to do some here. Resonance, because this cation is stabilized another way. Electrons next door. What's the charge of electrons? Negative, yes. Will electrons be attracted to positive? Yes. These electrons will tend to want to move in here and sort of bond. What does my arrow mean? WDAM. It means this is moving in to make a pi bond. To make a bond, the second bond will be a pi bond. Let's show that. Okay? Double-headed resonance arrow. And that arrow movement there gives Double bond to chlorine. How many lone pairs left on chlorine?
2.
2, because the other one moved in to make a bond. I'll draw in the new H if you would like. And where's the charge now? Because there should be a charge. The chlorine is now positive. This is just a progression arrow. That means this leads to this. That's a mechanism arrow. All we did in going from here to here was move pi electrons. And if you only move pi electrons, you're drawing a resonance structure. If you do anything with sigma bonds, basically you have two types of electrons. Pi electrons, those are ones that are what type of orbitals? P orbitals. Is that lone pair in a P orbital?
No.
Yes, because anytime a lone pair is next to a P orbital, I don't want to be in a P orbital. We've got 2 P orbitals here. Everybody see that? It was covered during test 1. Okay? Over here, we made sigma bond to H. Sigma bond, ain't doing resonance. Sigma bond to H. Whenever we go from here to here, are these resonance structures? No. We're making sigma bond from chlorine to carbon. Sigma bond, no. Here, pi bond, P electrons. This is resonance. Resonance structure. Okay, what does resonance do for you? It gives you more bonding. Importantly, it also delocalizes the charge. The charge is not just on carbon. The charge is also on the chlorine. If we can spread the charge around, that's a good thing. Which structure do you like best, left or right?
We got to pick between the 2.
So for that,
Let's answer this question first. Which do you like best, left or right?
We have to pick between the 2.
We have.
Because it's resonance, we have to pick between the 2, right?
That's a loaded question. Just on the board we do. In real life, you don't. Okay, resonance has many discussions. It's like colors. Pink is a blend of red and white. Okay? When you look at pink, do you see red and white or do you see pink? Right. Okay? But you know it can come from a blend of red and white. That's what resonance is. Whenever we look at those two structures, it's really only one structure. That's red and white. The true structure is pink. Problem is that pink thing is hard to draw. And so we show red and white and say, hey guys, the true structure is somewhere in between. It's a blend. It's like if I came in here and showed you, hey, this is red and white. The true color is pink. Can you imagine pink? And you would say, of course I can, because I know what pink is. Well, you need to say the same thing for resonance. I say, you see these two? Can you imagine the blend? You'd say, of course I can, because I know what resonance is. Okay? Color. So when you say, what was your question, your comment again?
I said, is it more appropriate to pick between the 2 and that there's really a partial positive and a partial negative charge because it's
You
resonance?
changed your comment.
I said we have to pick between the 2 because
Okay,
it's-
pick between two. When you look at pink, do you have to pick between red and white? No, it's just pink.
Right.
So this is why I said it's a loaded question, because I don't know how to answer it. In the end, yes, we will pick between the two. But in real life, no. Because in real life, you don't look at pink and say, red or white. All right, that's just me talking. So, again, I don't know how to respond to your question. We will decide between the two. Sounds really fake, though. Which one do you like better?
Left.
I heard some left. Who likes the right? Who likes the right? Yes? Yeah, everybody? Good. Okay, now here's the major. So the major resonance structure, this one's called the minor. Why is that one better? Major means it's better, it's lower in energy, it's the best structure of the. Okay? Why is the one on the right better?
More stable.
I already told you one answer.
Delocalized.
More what? Well, that's what major means. Major means it's more stable. Remember Bill Gates, why is he rich? You don't say because he's got a lot of money. Saying more stable is just, well, then I have to say, why does Bill Gates have more money? Why is that one more stable? Got what? Get rid of the pie and say it again. It's got more bonds. Do I agree the one everybody's got more bonds? Because we just made another bond right here. More bonds. Yes, that's why it's a better structure. Why did someone say that one was better? It is stabilized by the chlorine, and we show that here. Why did someone say that? There is a argument for that one being better.
Because chlorine doesn't like having that positive
Thank
charge.
you. Chlorine's pretty electronegative. It doesn't like being positive. So that's an argument why this one is not the best, but that's not the winning argument. But it's very reasonable. It's okay to make arguments that are very sound that are just ultimately not right. No, it's okay. The response would be, that is an excellent argument. The problem is, it's just not right because we know like certain data or facts. But your argument makes a lot of sense. Never be afraid of making a good argument, even though it may turn out to be proven wrong by data or experiment. Yes, chlorine being positive is a good argument for that being bad. But we actually know, and I can't tell you all the reasons why, but this is called major, and the main reason why is because it's got more bonds. So that's a conflicting argument. That's a counter argument. Question?
I thought that pi-bonds were more unstable than single bonds.
Yeah, otherwise they're the same. The only difference is they got all the same bonds. The difference is that's got an extra pi bond. Pi bond is a bond. We're not saying that one has a pi instead of a sigma. We didn't change any sigma bonds. We took the same thing and just made an additional pi bond. We're not comparing pi and sigma. Okay. Resonance. That's the main reason. That's the more important. You get the answer from just being secondary. Resonance is important here. Okay? Questions?
So if that's the major product, then how would
Not a major product, it's a major resonance structure.
medium resonance?
Okay? We'll talk more. Okay? You started your reading. Guess what? During test 3, we will officially cover resonance. We were supposed to already do it during test 1, but remember I told you guys too early. You'll build, you talk, you read. Hey, let's cover resonance. Question?
So for that chromatin ion, it's got the p orbital. That's an empty p orbital, right?
Empty p orbital.
So I don't understand why there are no pi bond forms. Both will one electron be in one, the p orbital of the
No,
carbon.
let's draw the structure here. I'm just going to draw. Yes. There's no H here. There's an empty p orbital. Let's just draw it. It's empty. It's sp2 with an empty p orbital. You got lone pairs up here. Guess what? One of these lone pairs is going to be in a p orbital. Why? Because there's one next door. Let's put one of these in a p orbital. Let's put the others in a hybrid orbitals. And the lines are supposed to be trigonoplanar, and the p orbital is the trigonoplanar. Both are trigonoplanar, and then both have p orbitals. Okay? That has a lone pair. Guess what it's doing? It's interacting with the neighboring p orbital, like we said it would during test 1. And what does this look like when you have two p orbitals interacting? Pi bond. I don't see a pi bond here. Well, guess what? I see it here. Now, what's the true structure? Remember, this is red and white. What's the true structure? Pink. The true structure is somewhere in between. So is it a double bond between the chlorine and the carbon, or a single?
The dash.
It's a bond and a half. It's like half a pi bond. You see, why is it a half a pi bond? Because the chlorine doesn't like totally giving the electrons up. I'm the chlorine and you're a positive. First off, we have a sigma bond, but let's forget about that. You're a positive and I got a lone pair. Ooh, physics, lone pair. Ooh, I'm attracted. But not too much, because I don't want to give you all my electrons. So let's just make a pinky bond. I'll give you some electron density. And that's what you got here. The true structure is sort of a bond and a pinky bond. a bond and a half. What's the blend of a single and a double? 1.5. BO equals 1.5. Bond order. And there's your pink thing over there. The pink thing is going to have partial bonds. They're a little bit harder to draw. What we do is we draw the red and the white. We talk about it blend. Sometimes we'll draw the blend. That chlorine is given some electron density, but it don't want to do a lot because it's electronegative. This is real life. This is how we do it on our board, our paper. Okay, we need to move ahead because we're not covering resonance right now. Semi. Questions? Okay. All right, so resonance stabilized, big thing, regardless. Another thing is, you can always use any resonance structure, and I'm saying some things with the tape because some things you just fly by, but when you rewrite the tape, you'll hear comments. You can always use any resonance structure in your mechanism. This chlorine can attack here. If it does, you get two chlorines bonded here. Or this can attack here. If it attacks there, you move these electrons back up. Either case, you get final product. You can always work with any resonance structure. Okay? Neither one is real. The true structure is what? Right here. By the way, we didn't talk about charge. We could do that if we want to talk about hybrid. What's the blend of neutral chlorine and positive chlorine? Partial plus. What's the blend of positive carbon and neutral carbon? Partial plus. There's your actual true structure. That's called the hybrid. That's the pink thing. The pink thing gets a little cumbersome to draw. We draw red and white and say, hey, what's the blend of red and white? Pink. Okay? That's resonance. Do some reading about it. All right? Okay, resonance. I told you that page of mechanisms where how to make bonds from nickel metal carbon backside attack or the other way, both sides. Very important. Okay, resonance is just as important, maybe even more important. Spending time on resonance will not be a waste. Okay? All right? As you approach the end of Organic 2, you'll be doing lots of resonance. Okay? It's like me telling you, hey, guys, learn how to multiply as you move forward in math. It will help you. All right? You think multiplication is important? Yeah, resonance is important. Spend some time on it. Okay, let's move ahead. Geminal dihalide. Vinyl cation. That's what we made here. Vinyl is slang for alkene. This is the cation on an alkene carbon. Vinyl cation. Some books don't like to show these, and they start talking about other things. I'm not going to take us there. I'm going to do it similar to alkenes. Okay? But you may see somebody say, never make a bisphenol. Never make a vinyl cation. They're actually kind of bad because it's sp. Other carbocations are sp too. And if you think about it, sp makes it worse, not better. All right? How about reaction with halogen? Elemental halogen like Br2 or Cl2. We can add a bromine to each carbon, yeah? But we're left with an alkene. We'll look at the mechanism. But if you started from here, could you show that product? Does that product look reasonable? Because that's an alkene, right? And alkenes react with bromine. We put a new bromine on each carbon. You did that reaction in lab. Okay? We'll come back here. Any stereochemistry here? Do you have a carbon or a stereogenic alkene? No stereochemistry. As long as you got two bromines on each carbon, that's it. What about over here, though? It will be E. Why is it E and not Z? This alkene is stereogenic.
Because
Here you are. This is actually linear over here. 1, 2, 3. Yeah. Okay, question. Is that actually formed in this case? Or does the new thing have a lone pair? Has a lone pair, not actually formed. And we can show something that looks like this. Yeah? Everybody agree? Similar to alkenes? We just have double bond here. This looks a little ugly. I'm doing it. Somebody might want to say something about it. My response would be, let's say something about it in organic 4 or 5, okay? This is organic 1. Let's kind of keep, all right, similarities. Everybody good? How does the, now we formed another Br minus here. How does it attack? We're going to attack and kick that back off. How does it attack?
From the back.
That bond's down, this bond comes in from the top, kicks that off. Many of you are not showing the second arrow here. Mechanism arrows show making and breaking of all bonds. I'm making a bond between bromine and carbon, but I've got to show this bond being broken. These electrons move back from the bromine as the third lone pair. And you see that this bromine will be up and that bromine will be down. Our original question is why? Because of the mechanism. Z would be where both bromines are up. You don't get that because the mechanism involves backside attack on a bridged bromonium ion. Yeah? Okay? So it should be pretty straightforward, analogous to alkene reactions. 2 equivalents. First equivalent gives this type of structure. It is stereogenic, so we can say is it E or Z or both. It will only be E. But when we add bromine again, we get this structure. It's a tetrahalide. Yeah, there's 4 there. But there's no stereochemistry now. And if you have no stereochemistry, you don't have to show projections or anything. Because there's only one way to connect things. As long as you have 2 bromines on that carbon and 2 bromines on that carbon, that's it. Yes, each carbon's tetrahedral. You're welcome to show bromines forward or back. Doesn't matter how you, all right? You get that discussion? Just like my hand. You can show a hand, right hand with a thumb forward. You can show the right hand with a thumb back. Show however you want. There's no other choice. Okay. There you go. You see the similarities to our alkene reactions? Okay. We'll be moving ahead. Please look ahead, particularly at tautomerization, which will be new. Tautomerization. That's it for this week, yeah? Well, the day's not over. You going to get something done today?
Yes, sir.
Okay, so Monday will be here soon. Okay, what's due Monday? Anything?
Loud.
What's that? The polarimetry lab? Okay. And I don't have anything to return today. Anything else, guys? We got tests coming up. This is our last handout here before the test. Alkyne chemistry. Please be looking ahead. Have a good day, guys. Have a good week.